Hello, welcome everyone. In today's lecture, we are essentially going to look at two fairly simple examples that involve stress concentrations and fatigue. Okay? So effectively, by the end of this lecture, you will be able to examine the failure of flat plates due to stress concentrations that arise from circular holes, and then you will be able to determine the number of cycles to failure in shafts that are subjected to fatigue and cyclic loading. Again, these are fairly simple examples that will essentially make it a little bit more clear for you on the concepts that we learned regarding stress concentrations and fatigue previously. Okay, so let's start with an example on stress concentration. Okay, so in this case, we are essentially given two flat plates. Both have the same width W equal to 100 millimeters. They have holes of different diameters. This D1 is 20 millimeters and this D2 is 50 millimeters. Okay? And these two plates are subjected to two different stresses, sigma 1 and sigma 2. And it's given that sigma 1 is equal to 1.5 times sigma 2. It's also further given to us that they are made from the same material, okay, and the stresses are uniaxial tensile stresses. Okay? And we are asked to find out which particular plate will actually fail first. Okay? And we are also given this KT versus DOW curve for flat plates. Okay? So in this case, you essentially have two plates that have identical widths but have different size holes, but they are also subjected to different stresses or different far field stresses. Okay? So there are a few things that you have to keep in mind. Okay? So the first thing we have to figure out is that what is the maximum stress in plate number 1? Okay? Of course, it is going to happen near the circumference here, okay, at essentially those 2 points. That is where you're going to have the maximum stress. Okay? But then the maximum stress in this case, in actually both the plates, depends on both the stresses that are applied far field, sigma 1 and sigma 2, and also the DOW ratio. Essentially, we have to consider both in figuring out what is the maximum stress in each plate. Okay, and that is what we're going to do now. Okay, and given that both these plates are made of the same material, essentially whichever plate has the higher maximum stress, that is more likely to fail first. Okay, that is how we are going to solve the problem. Okay, so the first thing we have to know is that sigma max is the stress concentration factor Kt times sigma nominal. Okay, and the sigma nominal is nothing but the far field stress sigma naught times W divided by W minus D. Okay, this factor W by W minus D essentially accounts for the reduced cross-sectional area where the plate is or where the hole is. Okay, so for the first plate, we are not given sigma, what is the value of sigma, but we are given that sigma 1 is 1.5 times sigma 2. So that is something we are going to use. But we do know that the width is 100 millimeters and the diameter of the hole is 20 millimeters. Okay, so essentially you can find out what the DOW ratio is, which is 0.2. And if you go and look at the stress concentration chart here, if you go to a value of about 0.2, the actual value of stress concentration about 2.52. Okay, so that is the value of Kt. Okay, so that is what I have used here. Okay, so Kt, which is the stress concentration factor for the first plate, is 2.52. Okay, now the nominal stress you can again find out is going to be sigma 1 times 100, which is the width, divided by 100 minus 20, which is 80. So essentially, the nominal stress in the cross section is 1.25 times sigma 1. Okay, so now you multiply the nominal stress at the cross section with the stress concentration factor, and you essentially find out that your sigma max in the first plate is essentially 3.15 times sigma 1, which is the far field stress. Okay, so essentially what you have done is we have found out what is the maximum stress in terms of the far field stress for plate number 1. Okay, we are going to do the exact same thing for plate number 2. Okay, in the second case, the width is still the same, but the diameter is larger. So DOW is 0.5. So we find out what is the KT2 value corresponding to that, and that is roughly around 2.2. Okay, so essentially the stress concentration factor for the second plate is smaller than the stress concentration factor for the first plate, which is expected because the diameter of the hole is larger for the second plate. Okay. Now, once we know what KT2 is, we can find out what the nominal stress is. And if you do that, in this case, the nominal stress is 2 times sigma 2. Sigma 2 again is the far field stress. So the maximum stress in plate number 2 in terms of sigma 2 is the nominal stress multiplied by the stress concentration factor 2.2, and that turns out to be 4.4 sigma 2. Okay, so what we have found out is that the maximum stress for the second plate is actually 4.4 times the stress that is applied far field. Okay, but that doesn't immediately tell us which plate is going to fail first. So essentially, we have to compare these two maximum stresses. Okay, for that, we can use the fact that your sigma 1 is given to be 1.5 times sigma 2. Okay, so we already found out what the exponent for sigma max in the first plate is, which is 3.15 sigma 1. Okay, so you replace sigma 1 by 1.5 times sigma 2, and that turns out to be 4.725 times sigma 2. Okay, and the maximum stress in the second plate is 4.4 times sigma 2, which essentially means that the second plate or the first plate actually has a higher maximum stress compared to the second plate. So since these two plates are made of the same material, the plate 1 is going to fail first. So that is our reasoning. Okay? So essentially what we did in this case was that we found out the maximum stress in both the plates, and then since these plates have the same material properties, we essentially figure out which plate has the higher maximum stress, and that is the one that is going to fail. Okay. Now, if these plates were made of different materials, then you essentially have to find out which one has a higher safety factor. Okay, so if the plate number 1 has maybe a larger yield strength or ultimate strength, then it's possible that plate 2 might still fail first. Okay, so in this case, the material properties are the same, so we don't have to worry about that. But if the material properties were different for the two plates, then essentially you have to take that also into account. Okay, so that is a fairly simple example on using stress concentrations and the concepts that you learned. Now we look at, again, a fairly straightforward example on using the concepts that we learned in terms of fatigue. Okay, so in this case, you're given that a steel shaft is subjected to 50 MPa of completely reversed loading. So what does it actually mean? Essentially, if you look at the maximum stress in the shaft, it essentially has a profile like this. Okay. Okay, so this maximum stress here is 50 MPa, and the minimum stress is minus 50 MPa. Okay, so this is the most stress point in the shaft, and it is subjected to this completely reversed loading. So which means that the maximum stress is exactly the negative of the minimum stress. Okay, so there is no mean stress. That is what it means. Okay, okay. So it is subjected to this 50 MPa stress, and in this particular case, it fails after 50,000 cycles. Okay, so essentially, if you apply a maximum stress of 50 MPa and completely reverse it, okay, then the shaft fails after 50,000 cycles. Okay, then you're given that the endurance limit of the shaft is half of its ultimate strength, which essentially means that your SE is 0.5 times SUT. Okay, so it's half of the ultimate strength. Okay, okay. You're given these two pieces of information, and you're asked to find out the ultimate strength SUT and the number of cycles to failure when a completely reversed loading of 40 MPa is applied. Okay, so there are two things that you're asked to find out. Okay, you are given two pieces of information. One is that if you apply 50 MPa of completely reversed loading, it takes 50,000 cycles for the shaft to fail. And you're also given that the endurance limit is half of the ultimate strength. You're now asked to find two things. One is the ultimate strength of the shaft, and also predict the number of cycles it will take for the shaft to fail if you now reduce the loading from 50 MPa to 40 MPa. Okay? So in a situation like this, the first thing that we have to consider is what regime we are in. Okay? So if you recall our discussion of fatigue, when the number of cycles is less than 1000, essentially the fatigue strength does not change with the number of cycles. At the same time, when the number of cycles is more than 1,000,000, then the fatigue strength again does not change with respect to the number of cycles. However, in the region between 1,000 cycle to roughly 1,000,000 cycles, the fatigue strength lowers or gets smaller as you increase the number of cycles. Okay? In this case, you are given the information for 50,000 cycles. So clearly, that particular number of cycles falls within the range where the fatigue strength is dependent on the number of cycles. Okay? So which means that we can use the logarithmic relationship between SF and N. Okay? And that is what we are going to use first. Okay? So essentially, we can use this formula because in this case, 1000 is less than N is less than 10 to the 6. Okay? So that is why you can use the logarithmic relationship. Okay? Now, if you look at this logarithmic relationship, it says SF is 0.9 SUT the whole square divided by SC times n to the minus 1 over 3 logarithm of 0.9 SUT by SC. Okay? If you don't get too bothered by the form, essentially you figure out that this SF is of the form SF equal to A times n to the power B. Okay? So where A is given by this factor here and B is given by that factor there. Okay? Now essentially using this particular equation, you can get a relationship between SF and N. Okay? However, there are some unknowns here. Okay? If you look at this particular equation, we don't know what SU2 is and we don't know what SE is. Okay? So how are you going to find that? Okay? Well, we are given another piece of information, which is that SUT over SE is 2 because SE is half of SUT. Right? Now, using this information, you can actually make some progress. Okay? So what I'm going to do is, essentially, I'm going to write this equation a little bit differently. So I'm going to say SF is 0.9 square times SUT times SUT over SE times this factor. Okay? And I'm also going to look at this particular SUT over SE. Okay? Now, if SUT over SE is given to be 2, I can essentially replace this factor by 2 and I can replace this factor by 2. Okay? Now if you look at the equation, essentially there is only one unknown, which is SUT. Okay? Which means that from the given information that the shaft fails at 50,000 cycles, when you apply a completely reversed load of 50 MPa, I can essentially get my SUT. Okay? And that is what I'm going to do now. Okay? So essentially, I write the equation in this way. Okay? And use the fact that, so this is actually 50 times 10 to the 3, not 10 to the 6. Okay? Then essentially you can find out what SUT is from this equation. And SUT turns out to be 77.5 MPa. Okay? And if you make the calculation for SE, which is just half of SUT, you get SE to be 38.75 MPa. So essentially what you have done here is essentially calculate the material properties, the ultimate strength and the endurance limit, using the fact that it takes 50,000 cycles for the shaft to fail when you have a completely reversed loading of 50 MPa. Okay? Now, once you know SUT and SE, you can also find this A and B. Okay? Remember, this SF is nothing but A n to the power B. Okay? So essentially, once you know SUT and SE, you can find out what A is and you can find what B is. Okay? Now, once you find A and B, we can essentially find out what is going to be the N if you are given what SF is. Okay, so in this equation, essentially you need to find A and B. Once you find A and B, at least for this particular region where n is between 10 to the 3 and 10 to the 6 cycles, you can essentially use this relationship here to find out what is the fatigue strength for a given n, or if you are given a particular value of stress that you're going to apply, you can find out what the number of cycles to failure is going to be. Okay, and that is what we are going to do next. Okay, because in the second part, essentially you're asked to find out what is the number of cycles to failure when the stress that you're applying is reduced to 40 MPa. Okay, so essentially when a 40 MPa load is applied, essentially your SF is 40 MPa. Okay, so again, I think I made a mistake here. This is actually correct. This is 10 to the 6. Okay. So again, I think I made a mistake here. This is actually correct. This is the stress, not the number of cycles. Okay, it is actually 50 into 10 to the 6, which is 50 MPa. Okay, so I made a mistake there. So this is going to be 40 MPa here, and that is going to be the A n to the power B. Okay, so this factor 125.54 times 10 to the 6, that is your A, and this is your B. Okay, so now once you have this equation, the only unknown here is n. Okay, and if you calculate what n is, it turns out to be n is about 686,000 cycles. Okay, now what you see here is that when you reduce the number of reduce the stress from 50 MPa to 40 MPa, so you're just reducing it by a factor of essentially 0.8, right? So you're reducing it by 20% basically, right? But now the number of cycles to failure goes from 50,000 to more than 686,000, which is more than a 10-fold increase. Okay, so what it essentially tells you is that even if you reduce the stress a little bit, the number of cycles you need to actually fail the material increases quite a bit, right? So that's why fatigue, even small increases in stress, can actually have a large effect on when the material or when the structure is going to fail. And the other thing that you must also note is that this value of n is still less than 10 to the 6 cycles. Okay, and that is important because if this value came out to be more than 10 to the 6 cycles, right, then you can no longer use this equation where SF equal to A n to the power B. Okay, so it is consistent in this case because the number of cycles turns out to be less than 10 to the 6 cycles. If it is more than 10 to the 6 cycles, then you can apply it because beyond 10 to the 6 cycles, your strength or the fatigue strength is going to be equal to SE. Okay, so you have to be a little bit consistent here. So you kind of make this calculation for n, assuming that n is going to be within 10 to the 6. If n turns out to be more than 10 to the 6, right, then you can't use this particular equation. Okay, usually that is not a case because we also know that your applied stress in this case is 40 MPa, and we calculated the endurance limit to be 38.75 MPa. Okay, so clearly the stress that you're applying is more than the endurance limit, so it is likely that it will fall under this range. But sometimes there may be some inconsistency. In that case, you need to be a little bit more careful. Okay, so this is again a fairly simple example on using the theory that you have learned in terms of fatigue to solve a problem related to a shaft cyclic loading. Okay, so again, there can be variations of this problem. For example, you could be given the endurance strength, the number of cycles to failure in two different loading conditions, and you can be asked to calculate SUT and SE. Okay, or you can be given SUT and SE and then asked to calculate directly what is the number of cycles to failure in a particular case. Okay, essentially, as long as you know in which regime which particular equation for the fatigue strength applies, then it should be relatively straightforward to solve problems like this. Okay, with that, I'll conclude this lecture. Thank you.